This is CS147 Computer Architecture Study lecture 14. In last lecture we talked about different aspect of system performance measurement. Uh, so this from this lecture and onward, like maybe 4 or 5 lectures, we'll be talking about how we can improve performance through architectural changes in the processors. So first one, which we'll be studying in little bit detail and little bit depth, is the pipeline architecture, and our topic will be covering this topic in next 2 lectures, like this lecture and next lecture 15. So today's topic is basically we'll look at the basic ideas of the pipeline for the performance improvement, and also what kind of instructions that architecture is suitable for pipelining. And then we'll start a topic which will continue next lecture as well, as a pipeline hazards. So basically we want to talk about like what are the different challenges in making a pipeline concept works in real life. So that's our topic is going to be. So pipelining for the performance, let's take a laundry analogy. Okay, let's take, there are 3 person A, B and C, and they have to do their laundry job. So one strategy can be, okay, A starts the laundry job and finish it, and that job contains like let's say 4 steps. One is washing, then drying, then stacking up the like those clothes and putting them back in the shelves. So these are 4 distinct steps it has to one has to complete to declare that laundry task is done. Similarly for B also will do the same 4 steps, and C will do same 4 steps for their clothes. Now if we think, okay, we are doing the laundry as a complete task, and A starts from one time and from 1 p.m. to 4 p.m. Let's say it takes like about 4 hours, like from 12 noon they start, person A starts on the laundry process, and each step let's say takes 1 hour each, then 4 step will take 4 hours, right? And once laundry is done for A, then B starts with their laundry, and it takes another 4 hours, so it goes on for the 8 p.m. and then basically another 4 hours for person C, and that person C will done at the 12 midnight. So total 3 person took 12 hours in total to complete their laundry process, right? 3 person total 12 hours it took. That means is throughput of the whole system, if you want to think in that term, throughput, it becomes like how many laundry, like we done 3 laundry in 12 hours. So we need to compute how many laundry you have done per hour, right? So that's the throughput by definition. So it will become like 3 by 12 laundry per hour. So it is basically 1/4 laundry per hour. That's the throughput of the whole laundering system. But if you see think very critically, that when A is done with the washing, that washer machine is basically free, right? Then B can start their washing at that point, right? And once B is done, then C can also start their process, right? And since each of these steps takes like an hour, then once A is done with the drying, then B can start drying immediately, right, after A, and so on and so forth. So then we can actually increase the throughput of the system with the strategy that instead of like waiting for the entire laundry to be completed, each of them take turns whenever the corresponding resources is free. Like when whenever the washing machine is free, next person starts. Whenever the drying machine free, next person starts. And in that case, in this way, what we can see that our total time for 3 laundry to be done become like 6 hour, right? From instead of 12 hour, it becomes a 6 hour task altogether. So throughput becomes 6 by 12, which is like half laundry per hour kind of throughput measurement. So we definitely improved from 1/4 laundry per hour to one and half, like, sorry, not one and a half, half laundry per hour, right? 1/4 laundry per hour versus half laundry per hour. So definitely we increase our throughput through this just change in the process, right? How we want to achieve it. So similar analogy we can make for the instructions as well. Let's take this example, like 3 instruction. Simple, like load word, and from like R1 to R0, we are loading like from a memory location. Address is determined by the R1 content with an offset, and R2 content and offset, and R3 content and offset, and that read of the memory will be stored in the R0. So practically this code doesn't mean anything, but just an example to elaborate the idea. So what we are doing so far in our processor, if you think of in terms of your project 2, you are executing one instruction at a time, and each instruction is involved in 5 standard steps: instruction fetch, instruction decode, register fetch, execute, memory, and write back, right? These 5 stages. So in that project also we assume that each stage will take 1 clock cycle. So essentially one instruction takes 5 clock cycle to be completed. So once one instruction is done, then we go with the next instruction, like instruction fetch, decode, execute, memory, and write back, and then next instruction go. So that way that processor works, right? That our processor works, and any basic processing model, any basic processor does in that way. Okay, this 5 cycle. Now it takes, that means since each of these instruction is involved in 5 clock cycle, that means 3 instruction will take straightforward 15 clock cycle to be completed. So in terms of throughput, that means if it will become like 3 by 15 instruction per nanosecond, if assuming that 1 clock cycle is 1 nanosecond, assuming that. So that means it is about 1/5 of instruction per nanosecond or per cycle, whatever you want to call it. So that's our throughput of the system. Now what if we could use the laundry analogy and just do this, like our instruction is executed in phases. Okay, so once the system done instruction fetch for the first instruction, and that instruction goes in the next phase, instruction decode and register fetch. During that time we start instruction fetching of the next instruction. Okay, and once the second instruction fetch is done, we start instruction fetch of the third instruction, and so on and so forth. And then instruction decode, execute, memory follows the same path. So if we could done this in this way, I'm not saying we can do it really, but our proposal is that let's try to put the laundry analogy here and execute these 3 instruction in this fashion, in this overlapped fashion. Okay, and that way, instead of taking like a total of 15 clock cycle, it would take like 5, 6, 7 clock cycle. Like 7 clock cycle it will take, which means 7 nanosecond, right? From 15 nanosecond it becomes 7 nanosecond. What about this strategy? It looks viable. It looks kind of promising that it can improve my throughput of the system, and in turn that means it is increasing the performance of the processor, of the processing system, right? So how we can achieve it? So before how we can achieve it, we take that, well, for what is the performance improvement or speed up in terms of execution time if we want to compute. So by definition, the speed up, and I kind of make it a little notation of maximum speed up. I'll tell you why in a minute. Anyway, the speed up is execution time in non-pipeline revision versus executing time of pipeline revision, and which is equals n, where the n is the number of stages or steps a complete instruction is executed. Like for in our case, it becomes n is 5, because we have 5 stages: instruction fetch, instruction decode, execute, memory, and write back, like 5 stages. So for us, n is 5. Let's say there are some other processor which can have 10 stages, 15 stages, even 40 stages is not very uncommon. 40 stage pipeline and 40 stage instruction execution. In that case, our maximum speed up is obtained is n. Now, why this maximum that suffix comes into picture? So our claim is, for a balanced n-stage pipeline, CPU is improved by n times, and that is the upper bound it can go. It is primarily because of the reason that all the instructions may not be started immediately after another in the pipeline fashion. Okay, may not be. There are dependencies, there are logical dependencies, there are structural dependency, and we'll talk about this towards the end of this lecture, and we'll continue that in the next lecture. And the term we call this is an hazard. Okay, so a perfectly balanced n-stage pipeline means there is no such hazard, and we're assuming we can perfectly overlap this instruction execution stages one over another, so that we can gain this speed up by n time. However, n is a theoretical maximum limit for a pipeline performance improvement. Okay. Also, pipeline increases performance by increasing the instruction throughput, of course, because if you look at the individual instruction, let's go back to this slide. If you look at the individual instructions, they will take 5 clock cycle individually, right? So what we are looking for, so they are not improving the number of cycle or amount of time needed to execute one complete instruction. What being improved is that during a unit amount of time, how many instruction I can be completing. I can complete. Okay, how many instruction I can complete. So in the pipeline way, like it apparently after the 5th clock cycle in this example, after that each clock cycle is a completion of one another instruction and so on and so forth. Let's say it's well balanced and we can all do this, like all of the instruction are executed in overlap manner in this way. So that means I'm actually increasing the throughput, though the individual instructions execution time remains constant. It's still 5 cycle, but overall, since we are overlapping those stages, we are increasing throughput of the system. So that's what it is meant by here. Pipeline increases performance by increasing instruction throughput as opposed to decreasing the execution time of the individual instruction. Now, this specific example, like we saw that E non-pipeline is 15 nanosecond and E pipeline is 7 nanosecond. So your speed up is kind of 2, almost 2, like a little more than 2. But we said this is a 5-stage execution, so we should have got at least near to 5 right, as a speed up. Why it didn't happen? It didn't happen because we are considering only few instructions here, like 3 instructions, right? Now take a more number of instruction. Instead of taking 3 instruction in our scenario, take like 1000 instruction. So 1K does, let's take it not 1024, but let's take as that as a 1000. So we are looking at 5000 nanosecond for an execution time on the non-pipelined circuit, whereas pipelined circuit total execution time in the pipelined structure will have 999 of the instruction will completed like one cycle after another, except for the first one. First one will still take 5 clock cycle. Then after that 5 clock cycle, next one will take another clock cycle, next one will take another clock cycle. We are talking about the balanced pipelining, and we can, let's say we can overlap all of them each other. There is no problem, no hazard, no interdependency on the instruction, and so on and so forth. So in that ideal condition, we have, like, except for the first instruction, every other instruction, this 999 instruction, will be completed one cycle after another, right? Will be completed one cycle after another. That's why it's become 999 cycles. Plus the first instruction will still take 5 clock cycles. So we are adding them up, and that becomes almost like 1004 nanosecond. Sorry, I dropped that unit, but it should read as 1004 nanosecond. Then my speed up become like 4.98, which is almost tending to 5. So if you can see that if we start increasing this number of instruction from 1K to 1 million to 1 billion, we'll go and start reaching towards the 5. However, we will not be able to reach that because of your first instruction will always take that 5 cycle, will take the extra 4 cycles there. So our speed up will go more near and near towards the 5, but it will never reach the 5. So that's the maximum theoretical speed up for a 5-stage processor that we can improve as if we just turn that processor implementation to a pipeline implementation. Okay, so that's the concept behind the performance improvement of a pipeline architecture.